Good afternoon, everyone. Welcome to the day 4 of online faculty development program on AI in cloud computing theory, practice, and application. So, in today's session, we are going to discuss about the resource allocation and task scheduling problems in cloud computing, and followed by we have another session which is about handling generative artificial intelligence at AWS Cloud Infrastructure by Professor Indrajit Gupta. So, in my last lecture, we have seen the implementation of task scheduling in cloud computing. Specifically, we have seen three different algorithms. One is the genetic algorithm, another is teaching learning based optimization, and Jaya algorithm. And later we are going to see another optimization algorithm in cloud computing, that is particle swarm optimization. But you can see there are numerous different problems we have in task scheduling and resource allocation. So some of the problems I will discuss in this particular session. So as the title suggests, it focuses on two topics. One is resource allocation, another is task scheduling. So you can consider resource allocation is the first phase. Once resource allocation is carried out, then we have to perform task scheduling. So resource allocation means suppose you need uh, 30 computers to execute a particular application, or you need to handle a particular project, or that you need a 30 computer system, then we call that as a resource allocation. So we need 30 computer system to run a particular job or particular application or a particular website and whatever may be, okay. But once these 30 systems are assigned to you, then you have to decide that which module is going to assign to which computer, okay. And also you have to see that in which order you are going to follow, what is the dependency between them. So that emerges the task scheduling algorithm. So the topics that are I am going to discuss will start with some of the basic concepts related to resource allocation and task scheduling. We'll start with the concept of leads, then application, job, and task. Although these terms are used alternatively, but the difference between these terms are, you can see they are different, right? But if you go to the dictionary meaning of these things, more or less they are the same. So we'll discuss about that. Some of the terms we are using in the resource allocation, some of the terms we are using in tax scheduling. Then we'll focus more on the resource allocation. Basically, I'm going to tell you about 5 different algorithms under resource allocation. We'll start with the base algorithm, that is Hygia. Then I will go about the next algorithm, that is DPS. Third one is ALTRA, that is alert time based resource allocation. Then I'll tell you a different problem in the resource allocation, in which we'll see what is a fairness based algorithm. Then similarly, we have another problem in which the solution is the posted price model. So this completes the resource allocation part if we cover these 5 different algorithms. Similarly, we have task scheduling problem. In task scheduling problem, we'll see multi-cloud scheduling. In multi-cloud scheduling, I'll tell you about 2 popular algorithms. One is round robin, another is cloud least scheduling. So we'll see in multiple cloud, there are different type of applications we have, and we have different arrival time, different mode of execution, and we use a different logic to assign the task to different cloud. Similarly, we'll see the workflow scheduling, in which we focus on only one application. We are not considering multiple applications. But when you go for multi-cloud scheduling, we consider multiple applications. So these algorithms I'll cover under the task scheduling, followed by the conclusion and reference. Now, if you go to resource allocation, as I mentioned, if you want to get some virtual CPUs from, let's say, in any cloud service provider, you may say Amazon is a cloud provider, or I can say IBM is a provider, or Google is a provider. So you'll place your requirement. Based upon your requirement, they are going to release that resources or provision the resources. So that basically we call as a resource allocation. But the alternate means the next to the resource allocation, we have another term that is called task scheduling. Scheduling mainly refers into two different processes. One is the matching, another is the processing or executing. So matching process, we found a particular resource for a particular task. Once you locate the particular resources, then you can dispatch your things to that particular resources. So that basically focuses on the task scheduling problem. So now you can see in these two terms, resource allocation and task scheduling, we have different terms. One is lease, another is application, another is job, another is task. So lease basically indicates a formal document where a user has to specify some of the requirements. But in the case of job and task, we don't have any such type of agreement. And we have applications. Application is normally represented in the form of a directed acyclic graph, or we can say that it is a data flow graph. And job is a collection of tasks, and the smallest unit of job you can say task, or you can say subtask. So in that way, these terms are related to each other, or they are differing from each other, right? And specifically in resource allocation perspective, we say lease. But when you see task scheduling terms, we say application, job, task. Sometimes we say meta task. Sometimes we say also subtask. So this is the terms that we are going to discuss while we are going to see different type of algorithms under resource allocation and task scheduling. So in order to understand the resource allocation concept, so I have considered a 4-node cluster. So you can see here the x-axis represent the time and y-axis. Okay, x-axis represent the time and y-axis represents the node. So we have taken a 4-node cluster. So node 1, node 2, node 3, node 4 are represented in the y-axis, I can say. So over a period of time, many user requests will reach to you and you have to provide the resources. So we basically make a cluster. So not necessarily 4-node cluster, but when you go for the implementation of a popular resource allocation scheduling algorithm, so we generally consider a 4-node cluster. Okay, but you can go for n number of n-node cluster also to assign different type of DJs to this 4-node cluster. So over a period of time, you have to alert, like a particular user can ask at max 4 number of nodes. But if a user is asking you more than 4 nodes, so it is not possible, right? It is not possible to provide because maximum number of nodes is 4. So we cannot provide 6 nodes, right? And also over a period of time, different leases are going to occupy some of the nodes. So on that time, if another lease is asking the resources, that resource is also not practically possible, right? So there are different type of leases we have. One of the high priority leases is called as advanced reservation lease, which we call as AR lease. For example, a user has asked a lease which is in AR mode, and that lease takes 3 nodes, and the lease need to start at 1 p.m. and need to be over. Okay, need to complete before 2 p.m. So this is a requirement given by a particular user. So we need a advanced reservation list in which the start time is given as 1 p.m. and end time is given as 2 p.m. Generally, when we submit a advanced reservation list, okay, so we have to specify the number of nodes. Here, number of nodes is 3. You have to specify a specific start time, which is mentioned here as 1 p.m. and there is a specific end time. So the end time is 2 p.m. right? And sometimes also instead of giving the end time, okay, so we mentioned the start time is 1 p.m. and the duration is 1 hour. So 1 p.m. plus 1 hour, so we can consider that is a 2 p.m. Right? So advance reservation is a high priority list. Any leads which is scheduled, and if a lead is assigned, then we are going to abort it. Right? Suppose another type of lead is executing, and at the same time a AR lead is arrived to the system, we have to abort it. Now coming to another type of leads, which is you can say little bit lenient comparison to the advanced reservation, and we call that leads as best effort leads. Okay, and best effort leads can be available in two different types. One is primitive types, another is non-primitive types. Okay, so in primitive types means when you execute the best effort leads, and in between if a another lease is coming, like advanced reservation is coming, so that B lease is going to abort it, right? So that is called as a primitive. But if it is a non-permittable based effort lease, once you start your execution, it will continue, right? It will continue without any interruption, right? That's why based effort lease is categorized into primitive and non-primitive. So based effort lease case, we are giving the duration. If you remember in the AR case, I told you we are using the start time and end time, or start time and duration. But in the case of based effort lease, we are only considering the duration. We are not specifying any start time or end time. So whenever the resources becomes available, the cloud service provider has to start the best effort lease. So there is no specific time for best effort lease, right? So mostly we use primitive best effort leases. So while you are executing a best effort lease, if an advanced execution lease is arrived to the system, we are going to abort it. But non-primitive case, once you start its execution, best effort lease, if high priority leases are coming to the system, you are not going to abort it, right? Or you are not going to preempt it. So I'm showing you a situation where you can see a best effort leads has started execution in node 1. After executing the best effort leads for some period of time, then a advanced reservation lead is arrived to the system. AR lead is arrived to the system. So that AR lead has printed the best effort leads, and AR lead has started its execution, and it occupies 4 out of 4 nodes, right? So once AR lead is completed, then you can resume that best effort lead. So another thing you can notice here that once a best effort lead is assigned to node 1, so if it is printed, then it will be resumed in the same node only. Like here you can see once AR lease is completed, so best effort lease is resuming its work from the node 1. You cannot resume its work in other nodes because the files associated with that particular best effort lease, like the informations, whatever the temporary informations, whatever the variables, whatever may be, so all are in the node 1. That's why we are not moving from node 1 to node 2 to execute that best effort lease. There is another lease that is called as immediate lease. It is just like our advanced reservation lease. But the problem is that in advanced reservation lease, normally the start time and arrival times are different. But immediate lease, its start time, arrival time is same. What I mean to say here that immediate lease arrive to the system and it asks to immediately start it. Okay, without looking into whether the resource is available or not. Okay, so most of the time the immediate leases are rejected, right? Because when they are making a request, we don't know what is the resource availability. If resources are not available, then we are going to reject it, right? That's why immediate leases are rejected because it arrives to the system and immediately asking for the resources, which is practically not possible to provide. But if resources are available, then we can provide the resources to the immediate lease. But we have seen that the best effort lease is suffering, whether it is a permittable or non-permittable. If there is a frequent arrival of advanced reservation lease, okay, then best effort lease is frequently printed, right? So if best effort leases are frequently printed, So it will not be a good condition for the best effort customers, right? So it may lead to also starvation. So in order to avoid this starvation condition, so people have come up with another type of lease, which is called as best effort with deadline lease. Sometimes we refer this is a deadline sensitive lease also. So what it says, it is not specifying any start time, it is not specifying any end time. It specifies a duration and it also specify a deadline. For example, I can say I need 30 minutes of computation. You have to provide in your computer system, but in 30 minutes of execution you need to do by today midnight. So I have specified the duration. I have not specified what is the start time, what is the end time, right? So that's why this waste effort with deadline lease is very popular, and you can say it is a compact view. You can say compact one of the normal waste effort. Okay, it is reasonable lease, I can say, right? So best effort says that as soon as the resource becomes available, we are going to provide it. But best effort with deadline says that as long as my lease does not start or end any later than the deadline. Okay, we put the deadline. Before the deadline, you have to fulfill it. Either I can put a deadline at what point of time you need to start, or at another end, I can say I'll put a deadline that after this time you should not execute. This is the last time. That is deadline. So does not start, it may happen, or does not end, it may happen, okay, later than the deadline. So based upon that, you can put a uh, deadline. Before that, it need to be executed. Otherwise, the task is going to be rejected, right? There is another interesting lease that is called as negotiated lease. Like when we go to a market, we always bargain, right? So this bargaining negotiations, based upon that also, we have another type of lease. For example, here you can see a customer has requested one node to a cloud service provider, and the customer committed to provide $100. Okay, suppose I have requested a resources to Amazon, and Amazon asked me to pay $100. So I am ready to pay $100. But when the time comes for execution, Amazon gives me an offer because the resource is already occupied by other leaches. So it has requested me, instead of taking the resources now, can you defer it to let's say 4 p.m. Instead of taking the resources 3 p.m., can you defer it to 4 p.m.? And instead of paying $100, you can pay $50. I'm fine with that. So if the computational requirement of a particular customer is flexible, then definitely we can go for it, right? But if computational requirement is not feasible, we cannot go for it, right? Similarly, when you reach to this soon, this level, then the Amazon is again asking you, can you defer the deadline from 4 p.m. to let's say 6 p.m. and instead of $50, you can pay $25 also. That is fine with me. Similarly, Amazon again is providing a offer that instead of 6 p.m., if you change it to night 12, then you take the resource or you take twice of the resource. That is, instead of one node, I can give you two nodes. Okay, and you pay only $10. So it is also happens because sometimes the resources are not available, right? That's why we are deferring that we cannot provide now. Can if you shift, you give me less amount, or you give the less money, but I'll provide the resources, or I'll provide twice the resources. So that kind of negotiations happen between the user and cloud service provider. So if you go for a cloud toolkit, you can see there are different toolkits we have. We have Amazon EC2 is a compute cloud. We have Nimbus. We have Eucalyptus. We have Open Nebula. We have Hygia. So if you see Amazon EC2 or AWS environment, if you look, all the allocation policies are follows best effort leases. Right? They consider every lease as a best effort lease for resource allocation. And Nimbus and Eucalyptus case will consider immediate allocation policies. Open Nebula case best effort policies. But if you go for Hygia, Hygia is a open resource manager, and allocation policies used by Hygia is different allocation policies they are using the advanced reservation, best effort, and immediate. So you can submit the lease as a advance reservation or best preferred in IGA. So as it open source and it works in the Linux environment, so you can download the IGA into your computer system and run the base algorithm. Okay, like submitting some of the leases as advanced reservation or best effort or immediate, or you can take a file where only you can specify advanced reservation leases, not best effort, not immediate, or you can make another file only with best effort leases. So that type of experiments you can try with IGA Open Resource Manager. So this is all about the lease. Then we'll come to the second term which we are using in task scheduling, which we call as application. So application is generally represented in the form of a directed acyclic graph, okay, or a data flow graph. Like here you can see I have taken, I can say I am taking 6 different tasks. Okay, I am taking 6 different tasks A, B, C, D, E, F. But these are not independent tasks. These tasks are dependent tasks. Okay, as they are dependent tasks, as they are dependent tasks, so we have to follow some precedence constraints. Okay. For example, you can see I cannot execute B, C, D, B, C, and D before executing A. So once A is completed, then only I can start B or C or D. Similarly, once B and C is completed, then only I can start E. And once the C and D is completed, I can start F. So that's why it is called as a precedence constrained applications. Okay. Or data flow graph also you can say. So there is a dependency. We have to honor that particular dependency. Based upon the availability of the task, they can be assigned to the cloud. So the application ID is given as 1 and every application has a arrival time. Here the arrival time is given as 0. Okay. So you can simply create a urgency matrix. Okay. So if you create a urgency matrix, then you can represent a particular graph. So in which, for example, in this case, as a 6 task is there. So urgency matrix, if you look like a matrix, so the dimension of the matrix is 6 cross 6. In which, if there is a dependency, then you will write in 1. If there is no dependency, you have to write 0. Now, if you go to real life scenarios, in real life scenarios, you will find many real life applications. Okay, like previous one, I showed you a simple random application, but in this slide, whatever you are seeing, these are real life applications. For example, first application, if you see, it is called as montage. So montage is a real life application which is used in astronomy domain. Okay, so here each and every node is treated as some task or instructions that need to be executed by a computer system. So you can see here there are 4 tasks in the root. Okay, so then these 4 tasks are connected to 6 different tasks. Again, they are connected to 1 task, and so on, right? So the structure of these applications are different, right? So you have to write the code for it to generate different type of tasks using the monte structure. You have to specify the computation time. You have to specify the communication time as well. Similarly, if you look into the second application, which we call as epigenomics. So epigenomics workflow is used in biology domain. So you can see around, I think, 16 tasks, 20 tasks are there in epigenomics. Okay, so their structure is more or less it is a formal structure, I can say, or 1 by 1 structure. So it is a general structure, I can say, but real life applications are too complex, like montage and SIPST. Similarly, if you look into SIPST, it is used in the biology domain and it is too complex in comparison to montage and epigenomics. So when you are going to write a code, or if you want to develop a new scheduling algorithm or workflow algorithm, so you should focus on these applications. Okay, the structure of the application is more important. The computation time, communication time, these all are important in order to execute them in different clouds. And I am showing you another 2 application. One is called as LIGO, which is used in the gravitational physics. CyberSec is used in the earthquake science. So you can see the structure of every application is different. So once you run a particular developed algorithm, you may find your algorithm is working fine in, let's say, epigenomics, but not working in cyber sec, or performance is not better in the cyber sec. That's why there are variety of applications are given in the literature, right? So that we can understand their structure and we can process in a number of clouds. Okay, if you consider multi-cloud environment, suppose you are collaborating with 5 different cloud, so you can assign this task to 5 different clouds. Now, if you coming to the task, so task is can be a independent task and dependent task. As already I showed you a dependent task in the form of an application. So dependent task is represented in the form of a directed acyclic graph, or we can say it is represented in the form of adjacency matrix. But independent tasks are represented in the form of a simple matrix. Okay, adjacency matrix represents the dependency between one task over another task, but matrix represent independent task matrix represents that how much time it will take in different processors. That is shown in the independent task. And if you go for independent tasks can be executed in online mode or they can be executed in the offline mode. Okay. So online mode is called as immediate mode or offline mode is called as the batch mode, right? So online mode means whenever a task arrives to the system, you have to immediately execute that particular task, right? But offline mode means you will put in a batch, and once the batch is filled, then you are going to process it. So that is called as independent task. And the process of matching and scheduling. First, you have to match, right? You have to identify that which resources is more appropriate for a particular task. That is called as matching. Then once matching is done, then you have to perform the process of scheduling, right? So matching and scheduling together, we call that as a process of mapping. Okay, for scheduling, mapping is more important. In mathematics also, we have seen different type of function which we use for mapping, like bipartite graph. We know about on-to relationship, one-to-one relationship, subjective, or bijective. So many types of relationships are there, right? Similarly, mapping process is important in between the task and the resources. So in order to perform this mapping, first you will go for the process of matching. Once matching is done, then you have to perform the scheduling. So sometimes this independent task, which I told you, which it can be executed in online mode or offline mode. So these tasks are called as the meta task. Meta task means they are not dependent on other tasks, right? They are independent. So if the tasks are independent, it can be executed at any point of time. Okay, that is called as your independent task. So mapping independent task onto a heterogeneous computing suite is a well-known NP-complete problem if throughput is the optimization criterion. Okay. So you can see, like if you want to map independent tasks, if you take a set of independent tasks and you want to execute these independent tasks in different cloud, right? Suppose you are given with 5 virtual machines or you are given with 5 data centers or 5 clouds. So they are heterogeneous in nature. So their configuration is different. Their architecture is different. So if you are assigning these tasks into different resources, then it is if it is an independent task and you are assigning it to different processors, so it is a well-known NP-complete problem. It is proven NP-complete problem long back because our objective is to minimize the overall processing time or improve the execution, or we have to look into the throughput, which says that how many tasks you are executing with a time. So it is quite challenging. Now, if you see how much time a task takes in the different resources, so that is represented in the form of a matrix that is called as expected time to compute matrix, which we call as ETC matrix. Okay. So in order to generate this ETC matrix, what you have to take? You have to take a set of tasks, and each task has two properties. One is the volume of instruction, another is the volume of data. And you have two resource parameter. One is the processing speed, another is the related bandwidth. Like here, you can see I have taken 4 different tasks and 2 different resources. and the volume of instruction of this task and volume of data of the task are given. Similarly, resource point of view, we are given with processing speed and related bandwidth, and you can see the tasks are also heterogeneous, resources are also heterogeneous because their values are not matching to each other, right? That's why we call it heterogeneous computing. So when you go for homogeneous computing, then you can see all the resources will take same amount of time. But this is not true in this case. That's why we call that as a heterogeneous computing. So I am taking this ETC matrix. In that ETC matrix, you can see you can calculate how much time the task T1 will take if it is assigned to resource R1. Similarly, how much time it will take if I am going to assign to resource R2. For example, if you assign the task T1, okay, the task T1 into the resource R1. Okay. So how to calculate this ETC matrix value or execution time? So execution time is calculated as volume of instruction, volume of instruction, instructions divided by processing speed, processing speed plus volume of data divided by related bandwidth. Okay, so volume of instruction in this case it is 200. Okay, if I talk about T1 to R1, so 200 divided by 100 plus volume of data is 20 divided by related bandwidth is 10. So you will get 2 plus 2, you will get it is 4. That's why you're getting 4 here. So if T1 is assigned to R1, so it is going to take 4 unit of time. Similarly, if you calculate if T1 is assigned to R2, T1 is assigned to R2 means we can calculate 200 divided by 200 plus 20 divided by 5. So 200 divided by 21, 20 divided by 4 is equal to 5. So it is taking 5 unit of time. So you can see obviously resource 1 is better for the task T1 and resource 2 is taking a little bit longer time, right? Similarly, you can calculate how much time it is going to take for T2, T3, T4 into resource R1 and R2 respectively. And it looks like a matrix. I can say it is a task resource matrix, right? So row represent the task and column represent the resources. So if you want to look the properties of this particular matrix, this matrix is of three type. One is called as consistent matrix, another is called as inconsistent matrix, another is called as semi-consistent matrix. So consistent matrix means if a particular cloud is better for one of the tasks, so it is better for all other tasks. For example, you can see here, I am showing you a ETC matrix in equation 1, which represents a consistent matrix. For example, if T1 takes 10, 25, and 116 for different resources, so the minimum execution time is 10, right? So for T1, the best cloud is R1, right, or resource 1. So similarly, if you go for T2, you can see R1 is only better. TN case also, R1 is also better, right? R1 is only the better, okay, best machine you can say. So for all types of tasks, if one of the resource is performing better, okay, then we call that as a consistent matrix. But when you come to equation number 2, in equation 2 you can see for task T1, resource 1 is having resource 1 is taking less time. For task T2, RM is taking less time. For task TN, R2 is taking less time. So you will not find any peculiarity here, right? You are going to find, if you want to find any pattern, that you are not going to get, because some case resource 1 better, some case resource 2 is better, some case resource 3, resource 4, anything can be better. So that type of matrix is called as our inconsistent matrix. Similarly, we have another matrix that is called as semi-consistent matrix. So semi-consistent matrix is a type of inconsistent matrix in which a part of the matrix is consistent. For example, if I take a 5 cross 5 matrix, in that 5 cross 5 matrix, if I found that a 3 cross 3 matrix is consistent, so we can consider that as semi-consistent matrix. So for example, here you can see if you look into T1, T2, R1, R2, this 2 cross 2 matrix is consistent because T1 is taking T1 taking less time in R1, so T2 is also taking less time in R1. So if I consider these two tasks, then I can consider that is a semi-consistent matrix. Okay, so like that, different type of matrices are there. The reason of going for these different type of matrices is that your algorithm may be perform better in the case of consistent or inconsistent or semi-consistent case. Okay, so you may not perform better in all the cases. Some of the instances case you are going to perform better. Some of the other instances case your existing algorithm may perform better than your algorithm. So that type of concept you will get when you go for the simulation using these type of matrices. If you look into these three type of matrices, you will get different peculiarity. Now, if you go for the resource allocation problem, so in resource allocation problem, you are given with the lease ID. Okay, you are given with a set of leads, and each lease is having a lease ID, and we have a arrival time of each and every lease, start time of the lease, deadline of the lease, period of the lease, uh, and we are given with the number of nodes. Okay, lease ID, arrival time, start time, deadline, period, and number of nodes are given to you. And the problem is that given a set of resources or nodes and set of leases, the problem is to map the resources to the leases to the resources. Okay, that is called as our lease allocation, resource allocation algorithm. And our objective is that if we are assigning a set of leases, okay, then we have to see that how lease acceptance ratio is maximized. Or on the other hand, I can say lease rejection rate is minimized. Okay. So suppose you are assigning 10 different leads. So you have to see that 10 out of 10 leads need to be satisfied. Okay. Or if you see that 0 out of 10 leads are rejected. Alternatively, I can say, right? So lease acceptance rate need to be maximized, or lease rejection rate is minimized. That you have to check. So here I am showing you an example for easy understanding. Here you can see we are given with 7 different leases. Okay, their arrival time, start time, deadline, period, and their number of nodes. For example, if you go to the lease L1 arrived to cloud service provider at 8:30, and the start time of this lease is 9, deadline is 10:30, and the period is 40 minutes, and requires only one node. However, if you go to L2 also wants the time between 9 to 10:30, but it is asking a 30 minutes period, and number of nodes requirement is 3. So every leases are having different period and different nodes, and they arrive at a different period of time. Their start time and deadline is maybe different. So given this type of lease, this set of leases, what you have to do, you have to assign these leases into the resources such that lease rejection rate is minimized or lease acceptance rate is maximized. So let us see. So there are three algorithms that we are going to discuss under this particular problem. The first algorithm we'll discuss is called as Hygiea. So Hygiea suggests that when a lease is requested to the cloud service provider, then you have to find a single time slot. Single time slot means you can say here if I say L1, so between 9 to 10:30, you have to find a single time slot of 40 minutes. So if there is a multiple time slot is there, that is not going to be accepted. Single time slot you have to find for 40 minutes. But if a single time slot is not available, then you have to you have to perform rescheduling. Okay, you have to reschedule it. Okay, so while you are going for the process of rescheduling, you have to sort the leases based on the slack value. You have to sort the leases based on the slack value. So slack value is calculated based upon the deadline minus deadline, start time, and period, and the formula is D minus ST divided by P. Okay, that is our slack value. But after sorting the slack values in non-decreasing order, If you are able to find a slot, that's fine. If you are not able to find, then you have to roll back. And one of the enhancement which we can do is that instead of taking a single time slot, we will consider a multiple time slot. Okay. Or several time slot, which can fulfill the lease. But if it is also not satisfied, then finally a lease is going to be rejected. So let us see one simple example. So I am taking a 5 different leases here, and the first lease is asking the start time is 12 and deadline is 1320 and it requires 40 is the period and number of node is 2. Okay. So what I'll do, I can start the lease in any two of the 4 nodes. So I'm starting in node 3, node 4 for easy visualization. So if the lease is starting at 12 and it requires 40 minutes, so it will start at 12 and it will complete by 12:40. And it requires 2 nodes. Okay, you can see it requires only 2 nodes. But now a lease 2 is coming. Lease 2 is also asking within 12 to 1320, you need 20 minutes period and number of nodes is 3. So once you assign this lease L1, so you are left with only 2 nodes. So it is not possible to fulfill the requirement of lease L2. So lease L2 is going to start at 12:40, okay, and it will take 20 minutes. So it will complete at 1. Okay, it will complete at 1. Now again another lease arrived to system. It is also asking from 12 to 1320, but it is asking 4 nodes of 20 duration. So we cannot assign here because here only 2 nodes are left. Here only 1 nodes are left. Okay. So the earliest time where we can start L3 is that we will start from 1. So from 1 it will take 20 minutes. So it will complete by 120. Anyhow, it is fulfilling its deadline. 1320 is the deadline. So 1:20 p.m. So just in the deadline it has finished its execution. Now L4 is coming into the picture. L4 is asking in between 12:30, okay, to 13:20, it needs 1 node for 40 minutes. So if you start executing L4 here, L4 can continue up to 1, right? And the duration is only 30 minutes, but its requirement is 40 minutes. So it is not possible to assign L4 in this particular space. Okay. So as it is not possible because single time slot is not there, so we are going to calculate the slack value of L1, L2, L3 because these are the 3 leases that are overlapped with L4 start time and end time. So if you calculate the slack value, in the case of L1, the slack value is calculated as D minus ST by P. So D is here 1320 minus ST is 12 divided by P is 40. So it is nothing but if you calculate, it is 80 divided by 40. So you will get 2. Similarly, L2 case, if you see, it is 1320 minus 12 divided by 20. So you will get 80 divided by 20, you will get 4. Similarly, for this particular case, 1320 minus 12 divided by 20. So it is 80 divided by 20, it is equal to 4. Okay. So their slack values are already arranged in non-decreasing order. Means they are already sorted. 2, 4 followed by 4. So if slack values are already in order, so rescheduling is not beneficial. So if they are not in sorted order, then you can perform rescheduling and check that whether you can accommodate L4. Okay, whether you can accommodate L4 along with L1, L2, L3. So L4 is going to be rejected. Similarly, L5 case, it is asking from 1240, 1240 to 120, it is asking 2 nodes. It is also not practically possible, right? So even if you go for the slack value, it is also not possible, right? Because L4 is aborted, again L1, L2, L3 is there. So if you calculate the slack value, the same thing will come like L4. So L5 is also going to be rejected. So if you look into this particular problem, how many leases we have accepted? We have accepted 3 out of 5 leases. Okay. So out of 5 leases, only 3 leases are accepted and 2 leases are rejected. Okay, so lease is going to be rejected because their requirement is not fulfilled. Okay, so we can see another example here. If you see, instead of 5 leases, I have 7 different leases. So I can assign lease L1. It will, if it starts from 9 and it will take 40 units. So 9 to 940, it is taking 1 node. So we have assigned L1 here. Similarly, L2 case, it is starting from 9 and it is taking 30 units and 3 nodes. So we can start L2 along with L1, right? So L2 is assigned here, right? It will take 30 units, 3 nodes. When you come for L3, L3 is going to start at 9, but it is not possible to start at 9 because L1, L2 both occupied. So the earliest time we can start is 940, 930. Okay, 930 if it will start, it is taking 2 nodes for 30 minutes. So I can assign here. So it will complete 930 plus 30, it is going to complete at 10. Similarly, when L4 is coming to the picture, L4 is asking 9 to 40 minutes. So anyhow, 9 to, it is not possible. Earliest time that is possible is 10. So if you start at 10, 40 minutes for 4 nodes, so it will complete by 10:40, which violates the deadline. So L4 is going to be rejected. So when L4 is rejected, we will go for the process of rescheduling of L1, L2, L3. Okay. So if you reschedule it L1, L2, L3, okay, so that is based upon the slack value. So slack value can be determined here as 1030 minus 9 divided by 40. So it is 90 divided by 40, it is 2.25. Okay, here you can calculate 1030 minus 9 divided by 30. So it is 90 divided by 30. So is equal to 3, right? Similarly, here you can calculate, it is 1030, 1040 minus 9 divided by 30. So I'll get 100 divided by 30, I'll get 3.33. So these slack values are already in the sorted order. So that is not beneficial. So finally L4 is going to be rejected. Similarly, you can proceed with L5. L5 is asking from 10, it is asking from 10, it is asking 10 minutes. So we can provide here L5. So L6 case, it is asking from 10, it is asking 30 minutes. We can provide here 30 minutes, right? On L7, it is starting with 10:30, okay, and it is continuing for 20 minutes. So it will continue up to 10:50, right? So like that, you can assign different type of leases, or in this case, if you see the total number of leases, if you see it is 6, 6 is accepted out of 7 using the IGA algorithm. Okay, so IGA is the base algorithm that is given in this IGA Open Resource Manager. So in order to improve the IGA algorithm, there is another algorithm which is called as DPS, that is Dynamic Provisioning Scheduling Algorithm. So if you go for DPS algorithm, first we need to find the slack value. So previously you are finding slack value if rescheduling is required. Okay, in case of rescheduling only, you are going to calculate this rescheduling case only, you are calculating slack value. But here at the beginning you have to find the slack value. But if the slack value is less than 1.1, then you have to reject it. So for example, one particular lease, if it's let's say 9 to 10, within 9 to 10, okay, it is asking, let's say 60 minutes. So 60 minute slots. So the difference between D minus ST divided by P, if you calculate, you will get 1. So as the slack value is less than equal to 1.1, that is going to be rejected. But if slack value is 20, okay, sorry, if the duration is 20, so D minus ST by P will get 60 divided by 20, it is 3. So it is greater than 1.1, that's why it will proceed for line number 3. Okay, proceed with the next step, right? Otherwise it is going to be rejected. So next, if it is less than 1.1, then you are rejecting. Greater than 1.1, you are accepting for further checking. So first you need to find the single time slot. If single time slot is not available, then you have to find the multiple time slot. Suppose one particular lease is asking for 40 minutes, and let's say 40-minute slot is not available, but two 20-minute slots are available, but not consecutively. Okay, so obviously it will be not be consecutive because it is single time slot is not there. So in that case also you can take multiple time slot. Two slots of 20 minutes you can take, and you can fulfill the requirement of a particular lease. Okay, but still if single time slot is not found, multiple time slot is also not found, then we'll go for the process of rescheduling. So in the process of rescheduling, what we can do, sort the leases based on decreasing order of the node. So we'll see the number of nodes. Based upon the number of nodes, we are going to sort the leases, right? We have to sort the leases based upon the decreasing order of n. If the number of nodes are more, then you have to keep first. If the number of nodes are less, then you have to uh, put in last, right? Like that you have to schedule. So if rescheduling is also not successful, then we go for a process of backfilling. In backfilling, we say that if a particular lease which is present in the queue, but not in the beginning of the queue, okay, still his requirement can be satisfied. So that is called as the process of backfilling. And if rescheduling is not successful, backfilling is also not successful, we simply reject that particular lease. Now let us see the example. So I'm taking the same example where I consider 5 different leases. So we have successfully scheduled L1, L2, L3. If you remember, if I go back in the case of Hygia, here you can see I have already successfully scheduled L1, L2, L3, right? So only L4, L5 is not possible in the case of Hygia algorithm. So let us see, is it possible in the case of DPS algorithm? So as L4 requirement is not satisfied, okay, L1, L2 is all, L3 is already scheduled. L4 requirement is not satisfied. So L4 is requesting L1, L2, L3 for rescheduling, right? So when you go for the rescheduling process, you will reschedule based upon the decreasing order of n. So if you look into L1, L2, L3, okay, so the number of nodes, the highest node is L3, followed by the next node is L2, next node is L1. L3, L2, L1. L3 is 4, L2 is 3, and L1 is 2, right? So I am assigning L3 first, then L2 second, then L1 third. So earlier it is L1, L2, L3, but now it is changed to L3, L2, L1. Now we will keep this particular order subjected to L4 is L4 requirement is satisfied. So if you look into L4 requirement, L4 is asking 12:30, one node for 40 minutes. So if it starts at 12:30, if it takes 40 minutes, so it will complete at 1:10. So that is one node is satisfied. L5 case, so now L4 is satisfied after rescheduling. But in that case, if you remember, L4 is rejected. Now if you come to L5, L5 case, the start time is 12:40 and it will go for 2 node and 10-minute slot, right? So if it starts at here, let's say 1:10, so is it asking 10 minutes? So its requirement is satisfied. So using DPS algorithm, what we have seen that the 5 out of 5 leases are accepted. But in the IGA case, we have seen only 3 out of 5 leases are accepted. Okay. This is the only difference between the DPS and rescheduling criteria is slack value there. But here rescheduling criteria is our number of nodes. Based upon that, we are performing rescheduling. The third algorithm that we are going to see in the case of resource allocation is called as alert time based resource allocation. So in alert time based resource allocation, the main focus is alert time. What is a alert time? Alert time is nothing but deadline minus your period. For example, you have given the deadline is midnight 12, and if let's say you have given some assignment to your students, and let's say in order to solve that assignment, your student require minimum of 2 hours, and the deadline is given as let's say today midnight. So as the assignment takes 2 hours, so 12 minus 2 hours is 10 or 10, right? So the assignment need to start at 10 p.m. in order to complete it before the deadline. So that is called as alert time. So based upon alert time, we are going to assign the leases to different resources. So the first step of alert ALT array is that sort the leases based on the start time. So normally leases are sorted based on the arrival time. Okay, so here the leases are sorted based upon the start time. That means if a lease is having earliest start time, so that need to be sorted fast. Okay, that needs to be available fast. So once you sort the leases based on the start time, the second step is you have to form different groups with the same start time leases. For example, if you found that three leases are having the same start time, so you have to make them as a group in a single group. Then in that particular group, you have to find the alert time. Okay. So once you find the alert time of let's say three different leases that are present in one group, then you have to assign earliest alert time first. Okay. Out of these three leases, which leases comes first, that is you are going to assign it. But if there is any tie, if there is any tie happen between two different leads, then tie can be broken based upon the maximum number of nodes. Okay, and even if the maximum number of nodes, if there is a tie, then you will break it, right? But based upon the earliest alert time, while you are assigning the DJs, let's say you are not getting a solution, means we are not finding any slot. Then what you have to do? You have to perform the process of swapping. So in order to perform the process of swapping, you have to create three lists. One is start time to the alert time, another is alert time to the deadline, or overally it is start time to the deadline. So earlier we used to perform rescheduling and everything with respect to start time to the deadline, but now it is start time to alert time to deadline. Okay, we are not taking start time to the deadline, and it may happen that a particular lease slot is overlapping during STLT as well as LTD, right? So in order to overcome this, we are calculating the intersection of STLT and LTD. Okay, and so the reason of calculating intersection is that once you find the intersection, you will know what are the leases that are common during these two slots. So you have to again delete you have to remove that particular lease from a particular set so that the number of comparison is going to be reduced. That is the reason why we are doing this one. Okay, so if swapping is not successful, then we will go for the process of backfilling. Otherwise, we have to reject the lease. So let us take an example. So I am taking 7 different leases. Okay, I am here taking 7 different leases. They are L1 to L7. And I have ordered these leases based upon their start time. So you can see L1, L2, L3, L4, they are having the same start time. L5, L6 is having same start time, and L7 is having same start time. So now, if I calculate the alert time of alert time is calculated based on the group. So first we have to make group. So as first 4 leases are having same start time, so they are put in a group G1. And the next 2 leases are having the same start time, so they put in group 2. And there is another lease, that is L7, which is alone having a unique start time, so it is put in group 3. So in the worst case, what you can get that the number of leases is same as number of groups. Now if you look into group G1, in group G1 you have 4 different leases, right? You have 4 different leases. So you have to calculate their alert time. So if you calculate the alert time of L1, so L1 alert time is calculated as I mentioned, it is deadline minus period. So if I calculate alert time of L1, so it is 1030 minus 40. So you will get 950. Okay. Similarly, alert time of L2 is 1030 minus 30. So that is 10. Similarly, L3 case 1040 minus 30. So it is 1010. Similarly, L4 case, it is 1030 minus 40, you will get 950. Okay, so these are the 4 leases and their alert time we got. So I told you, once you found the alert time, you have to find the earliest alert time. Earliest alert time you are finding for L1 as well as L4, because both case there is a tie. 950, 950 is tied. So if there is a tie, what you will do? You have to select the lease with maximum number of nodes. So here the maximum number of node is 4. So L4 is scheduled first, then L1, then out of L2, L3, earliest time is L2. Okay, and the next earliest time is L3. So in this order, you have to assign these images to different resources. Okay, and if you ask me for second group, so in second group you have these two lineages. Alert time is, the earliest alert time is L6. So L6 need to be processed first before the L5. And L7 is alone, that's why L7 will be processed after that. So this order you have to follow in order to assign them into different resources. So let us see. So once you calculate the alert time, so I am assigning first is L4. So L4 took 4 nodes, okay, of 40 minutes. So it is 9 to 9:40. Then L1 is one node. L1 is one node for 40 minutes. Okay. So that is 9:40 to 10:20. Then L2, L2 is taking 3 node. Okay. And its duration is 30 minutes. So it is starting from 9:40, completing at 10:10. Then L3 case, it is taking 2 node. Okay. It is 2 node for 30 minutes. So if it starts at 10:10, so it will finish here at 10:40. Similarly, L5, L6 case, I need to process L6 first. L6 takes 30 minutes for one node. So it is starting here. Then L5, it is 10 node, 10 duration for one node, right? That is also satisfied. L7 is taking 3 nodes for 20 minutes. So if it starts here, then it will continue up to this, right? So now you can see 7 out of 7 leases are accepted in ALT array. Okay. So again, it depends upon the data set that which performance is going to be better, whether ALTRA or DPS or the J algorithm, right? But mostly you can see these two later two algorithms are performing better in comparison to the J. Now, how to evaluate this resource allocation algorithms? So there are different type of matrices that you have to use for it. So the first matrix we are using is accepted leases. So if you are given, let's say 7 different leases, you have to estimate how many leases are accepted out of 7. Similarly, we have to find how many leases are rejected. Okay. And then we are finding leases insisting rescheduling. How many leases are insisting rescheduling? Like we have seen, L4 has insisted rescheduling for L1, L2, L3. Right? In that 5 leases set, we have seen L4 is insisting L1, L2, L3 for rescheduling. So that will be counted under this one. And once it is insisting rescheduling, whether they reschedule or not, if they reschedule, they will count it here. That is called as number of rescheduled leases. So we have a data set in which we have 11 number of leases, 22 number of leases, 33 number of leases, and 44 number of leases. So if you run the data set and compare these 3 algorithms, or you can create your own data set by considering such a number of leases, and you can compare between these 3 algorithms and you'll find which algorithm is performing better. So this is all about the first 3 algorithm, which comes under a particular problem in which we consider that a set of leases are assigned to a set of nodes where lease rejection rate is minimized or lease acceptance rate is maximized. Now, the next resource allocation algorithm is called fairness. So we have seen different type of leases. We have seen advanced reservation leases, best effort leases, immediate leases. Then we have also seen negotiated leases. So if you focus on AR and BE leases, so AR is more priority, best effort is has less priority. Okay, AR is more priority and best effort is less priority. And frequent arrival of advanced reservation lease, if frequently AR leases are arriving, then it is going to impact the best effort lease, right or not? So if AR leases are there in the system, B will not never get a chance to execute. So it is not a fair solution for the best effort leases. So one of the obvious solution is that you have to go for non-primitive best effort. Okay. So once a best effort lease is started its execution, okay, you should not print it. That is one solution. On another solution, you can see a few best effort leases you have to schedule before the AR lease. Even if B is less priority, you have to give chance to some of the best effort leases before the AR leases, so that that problem can be solved. Now, if you take an example, suppose at t is equal to 0, a best effort lease BI is arrived in which the period is equal to 5. So it is asking for a duration of 5. So obviously you will assign 0 to 5, the best effort lease, that is BI, right? But at t is equal to 2, what we have seen, an advanced reservation lease AI is arrived to the system, which says that the start time should be 2 and period is 5. So if it starts at 2, it will finish at 7. And AR lease is having more priority. So AR has started its execution and best effort is aborted or printed. But once AR execution is over, then we can resume the work of the best effort lease, right or not? But at t is equal to 7, let's say another set of bed B leases arrive to the system. That is 2 B leases arrive to the system. And let's say 4 advanced reservation leases arrive to the system. So first best effort lease BI requires 5 unit of time. But after 2 unit of time, means remaining time is 3, you have started AR lease and AR lease is completed. So after immediately completion of this AR lease, I can start the best effort lease. So I'm starting BI. Okay, I'm starting the best effort lease. But at 8 unit of time, you can see an AR lease is coming. So it has to start at 8 and complete at 13. So again, this best effort is executed for 1 unit and remaining 2 unit it has to wait, right or not? So similarly, if you go for another advanced reservation lease, which is starting at 15. So you have a slot at 13 to 15. So this BI will get a slot here and it's executed its execution and it completes its work. But another two best effort lease, that is BJ and BK, is waiting, right? And immediately after BJ, we can start the next AR lease, that is AK for 3 unit of time. Then AL we have to execute for 2 unit of time. Then AM we have to execute another 3 unit of time. So AK, AL, AM is now successfully executed. Okay. So now once AR leases are executed, then you can start the BJ lease and BK lease. BJ will take 3 unit of time, BK will take 1 unit of time. So what you can see in this chart, the best effort leases are deferred if AR leases are arrived in the system. Okay, that makes that there is no fairness among the algorithm, right? So you have to design a resource allocation algorithm in which you can make a fairness, right? So you have to treat AR and B not equally. It is not possible to treat them equally because AR is always high priority. But at the same time, all the best effort leases should not face a starvation. Okay. So if every best effort customer faces the starvation, then nobody will like the best effort lease execution. Okay. Nobody submit its lease in best effort mode. So that is not good. So always we can say that let's say 20% of the best effort leases we are going to give priority. 20% of leads will push before the AR leads. Okay. So AR leads you will take 80%, right? But 20% you will give to the best effort leads. So at that time, if any advanced reservation leads arrive to the system, then you are not going to consider it. Okay, there is another popular resource allocation algorithm that is called as posted price model. This posted price model is based upon one of the famous algorithm that is called as Hungarian algorithm. Okay. So in posted price model, you are given with a set of tasks and set of clouds. And normally we consider the set of task is same as set of clouds. Okay, we consider set of task is same as set of clouds. That means this matrix is a square matrix, right? But normally, if you see, the number of tasks are quite more in comparison to the cloud number of clouds. So in posted price model, what we did, we consider a set of tasks which is quite more than the setup cloud. But before going to that particular structure, so I have to show you that how a simple Hungarian algorithm works. Once you understand that, you can take a case where the number of tasks are quite more in comparison to the number of clouds, right? So in Hungarian algorithm, first what we are doing, first we have to find the row minimum, and you can see TI to a particular task to the cloud and its performance measure values are given in the matrix. Just like I told you, consistent matrix, inconsistent matrix, and semi-consistent matrix, right? So if you find the row minimum, you will find in the first row the minimum one is 0.23, and once you find the row minimum, you subtract 0.23 from each and every element of that particular row. Similarly, for T2 case, the minimum is 0. So if you subtract 0 from all the elements, you will get the same element. Similarly, T3 case, the minimum one is 0.31. So you have to subtract all the elements with minus 0.31. Then you will get this particular value. So like that, you have to execute. We have to find the row minimum value and subtract that row minimum value from each and every row. So after performing this one, you will find at least one element in each and every row is 0, because the minimum element you have subtracted. That means at least one element you will get, that is 0. So which you can see here. Okay, at least one element you will get 0. But if there is, if it is the case where the minimum element is available in two different locations, then you will get two zeros, right or not? So once the subtract row minimum process is over, then you have to go for the process of subtract the column minimum. So you have to find the minimum of a particular column. For example, here you can see 0.11 is the column minimum, and this 0.11 is available in two locations. So I have to subtract 0.11 from each and every element. So you will get 0 here, right? So once you perform the subtract row minimum followed by subtract the column minimum, you have to see in your matrix, you can get so many zeros. And you have to cover these zeros with the minimum number of lines. Okay, obviously the maximum number of lines to cover all the zeros is 6. But you have to go for minimum number of lines to cover these 0 elements. So if you go for minimum number of lines, here you are getting minimum number of lines is 4. Right? So minimum 4 lines, as you can see, with 4 lines I can able to cover all 0 elements. But if number of lines, that is which is here, it is 4, it is not equal to number of rows. We want the number of lines will be equal to number of rows. But in this case, number of line is 4, number of rows means number of tasks is 6, right? So if it is not equal to, as number of lines is not equal to number of rows, then add the minimum uncovered element to every covered element. So which one is minimum uncovered element? You can see the minimum uncovered element is 0.08, which is available in multiple places, right? So we have to add this minimum uncovered element to every covered element. Covered element means which is striked out by the lines. But you can see there are 3 elements which you can see here. These 3 elements is covered twice by first line and then the second line, right? Okay, this particular line and this line. This is covered by this line and this line, right? So what you have to do in that case, you have to cover it twice. So if you go for this one, you can see the minimum element is 0.08. I am adding in each and every case. But where there is a one line is crossed with another line, so we are adding 2 times. Here we are adding 2 times, and so on. Right. So you have to find the minimum uncovered element, and that uncovered element you have to add to every covered element. If the covered element is covered twice, then you have to add it twice, right? So now once it is done, then again you have to find the minimum element through whole matrix, minimum element in the whole matrix. So the minimum element in whole matrix is 0.08, right? You can see here the minimum element you are getting here 0.08. That 0.08 you have to subtract from the whole matrix. Okay. So if you subtract from 0.08 from all the matrix, you will see all values are 0. Okay, all these values are 0. Okay. You can see most of the values are now 0. So After subtracting the minimum element from all the elements, you are getting all values are 0. So now what you will do? You have to again cover these all 0 elements with minimum number of lines. So in this case, if you see, the minimum number of lines to cover all the zeros is 6. Okay, if number of lines is same as number of rows, then we have to stop. Otherwise, you have to continue until unless the number of lines is equal to number of rows. So this is also one of the very popular model that is used in resource allocation. And you can also see once you find this minimum number of lines is equal to minimum number of rows, then you have to assign the task to the cloud. For example, you can see in this case, if I tell you T1 can be assigned to C2, T1 can be assigned to C4, C5, and C6. Suppose I am selecting C2. Okay. Similarly, T2 can be assigned to C4. This is the only option available. T3 can be assigned to C1. T4 can be assigned to C2, C4, C5, C6. But I'll assign to C5 because C4 and C2 already we have assigned some other task, right? T5 can be assigned to let's say C2, but it is not available. I can assign to C3, and T6 can be assigned to C6. So the idea of taking the number of tasks and number of resources is that you will get at least one task, actually exactly one task for resources. That is the reason why you are taking number of tasks is equal to number of resources. But when you go for a real life situation, you can see the number of tasks is not equal to the number of resources. In that case, you can start a dummy elements also to cover the whole matrix, and you can take a particular decision. So this is all about the task scheduling perspective. Now we'll go for this is all about the resource allocation perspective. Then we'll go for the task scheduling algorithm. So in task scheduling, what we are doing, we may project the task scheduling problem into a single cloud environment, or we can project the task scheduling into a multi-cloud environment, or you can go for a centralized approach, or you can go for a distributed approach. For example, here you can see I am showing you there are different clouds we have, like cloud 1, cloud 2, and I can say this is cloud 3 and cloud 4. So these clouds are integrated together to provide a unified service. So they agree to create a centralized manager, which you can see here. The centralized manager is coordinating all the tasks, and it is connected to all the clouds. So whenever a user has submitted a particular task, so it will come to the centralized manager. Or if a user is submitting a collection of the task, which we can say job or an application, so it will be come to the centralized manager. And centralized manager has information about all the cloud resources. So every cloud also is having a manager server. You can see there is a manager server in each and every cloud. So that manager server is responsible. Okay, the manager server is responsible. The manager server is responsible to track all the resources. Okay, whether the resources are free or they are busy. All these informations are with the manager server. So the centralized manager is in coordination with the manager server, dispatch the task to the corresponding cloud. For example, this customer's task, the centralized manager decided that I will send to the cloud 1. So before sending to the cloud 1, it has to consult with manager server and send it. So this is an example of a distributed approach. Okay, it is completely distributed approach. Sorry, it is completely, I can say centralized approach, not a distributed, centralized approach. All the clouds are distributed, but they are coordinated centralized. But if the centralized manager is failed, then the whole network is going to be collapsed, right? The whole network is collapsed. If this is not available, then all the clouds are not connected. We cannot provide a unified service. So in order to avoid this one, we can go for distributed approach. In distributed approach, what we will do, the customer has to submit the task to one of the manager server. Okay, earlier it is submitting a centralized manager, but now it is submitting to a manager server. And the manager server partition the application into small tasks. For example, you can see this is an application. Okay, A is the, I can say, root. After A is completed, you can execute B and C. And once B is completed, you can start D. And once C is completed also, you can start D. Okay. And another is E. E is executed after D and C. Okay. So this is an application. So when this application reaches to the manager server, a particular manager server, the manager server can check that whether it is possible to execute whole applications into its own cloud or not. So if it feels that yes, I can execute whole cloud, the whole task, whole means applications with that comprises of tasks, then the manager server will assign all these tasks to the waiting queue. It will be placed in the waiting queue and it will execute. But if manager server feels that no, all the tasks cannot be executed in our cloud, but we have to send to another manager server. Okay, so here you can see A and task D. These tasks are kept by this A and D, A and D. So it is kept by whom? By the cloud one. And the task E, or let's say B, C, so it is sent to other clouds, right? So that all will together can execute the task, right? So in this way, they collaborate each other and provide services to the customer. And customer can submit the request either in the advanced reservation mode or in the best effort mode, right? So for example, in this case, this application may be advanced reservation application or it may be best effort application. Okay, based upon that, it is going to be assigned. Okay, now I'll tell you two different task scheduling algorithm that are applied into multi-cloud environment. So here you can see we have three different application. One is application 1, 2, and application 3. And their arrival times are also different. Like arrival time of the first application is 0, arrival time of the second application is 3, and arrival time of the last application is 9. Okay. And each and every application is submitted in a particular mode. So I told you there is two mode or two leases I told you. One is advanced reservation lease, another is best effort lease. For example, this workflow is submitted in the best effort mode. This workflow is submitted in best effort mode. And this one is submitted in the advanced reservation mode. Okay. So first and last application is submitted in the best effort mode. That means the tasks that are under this best effort, okay, they can be aborted or preempted. But the tasks that are defined under advanced reservation, that cannot be preempted. Okay. So we are also calculating based upon the volume of instruction, volume of data, processing speed, bandwidth. We are calculating what is the expected time to complete a particular task on cloud. Like if you say uh, task A, if task A is assigned to cloud 1, then it is taking 2 units of time. But if task A is assigned to cloud 2, it is taking 3 units of time. But if it is assigned to again cloud 3, then it is taking 5 minutes of time. So this matrix is more or less, it is an inconsistent matrix, which I earlier told you. So you can see for task A, you can say cloud 1 is better. For task B, you can see cloud 3 is better. For cloud C, you can see cloud 2 is better. So we cannot make a conclusion that for all type of tasks, cloud 1 is better. We cannot say, right? So now you can apply different algorithms to solve this particular problem. For example, if you are applying the first algorithm, that is round robin. So we know in round robin, we assign the task to different clouds by following a sequential order. For example, I can assign the task A to the first cloud, task B to the second cloud, task C to the third cloud. And again, I'll execute the task D in first cloud and task A is the second cloud, right? Because we have 3 clouds. If it is 4 cloud, then D can be assigned to the fourth cloud. Similarly, if you come to F, F can be assigned to the first cloud, G can be assigned to the second cloud, H can be assigned to the third cloud, and I can be assigned to the first cloud. Okay. Similarly, J can be assigned to the first cloud, K can be assigned to the second cloud, and L can be assigned to the third cloud. Okay. So if I write in cloud 1 term, cloud 1, cloud 2, cloud 3, so I can say cloud 1 can execute task A task D, task F, task I, and task J. Okay. Cloud 2 can execute task B, okay, task E, task G, and task K. Cloud 3 can execute task C, task H, and task L. So I think total number of tasks, if you count, it is 12, right? But I cannot start A, D, F, I, J simultaneously, right? So based upon precedence, okay, based on their precedence, we are going to assign them into the cloud. So for example, A can be started 0 unit of time, but D's cannot be started at 0 unit of time. D can only start once B and B is completed. Okay. Similarly, F can only start at 3 unit of time, not before that. Okay. I can be assigned only once G is completed, and J can be executed at the arrival time 9. Okay, like that you have to assign them into 3 different cloud, and you have to calculate what is the overall completion time. Overall completion time. So overall completion time is called as make span. Okay. For example, you are getting overall completion time that are assigned to the tasks that are assigned to cloud 1 is, let's say, 25. The overall completion time for executing all the tasks here, it is, let's say, 22. And the overall completion time for executing all the tasks that are assigned to cloud 3 is 20. So we are calculating the make span based upon the maximum value of 25, 22, and 21. So I am getting the value as 25. Okay, because until unless all the tasks means what are the tasks, tasks are available in 3 different applications, they are not completed, we cannot say our job is completed. That's why we are calculating maximum of 25, 22, and 21. That is 25. And once you determine the make span, you can calculate the resource utilization. So resource utilization is based on what is the local make span, okay, divided by the overall make span. So local make span is here 25 for cloud 1. If I calculate cloud 1 case is 25 and overall make span is 25. So utilization is 100%. But C2 case, it is 22 is the local make span and overall make span is 25. C3 case, it is 20 divided by 25. Right or not? So you will get, I think, this 4 by 5. Okay. So if you calculate average resource utilization, average resource utilization. If you calculate average resource utilization, it is 25 plus 22 plus 20 divided by 3 into 25. That will give you the value, right? A particular value it will give. Okay, and if you multiply with 100, you will get in percentage. So you have to calculate this for round robin algorithm. Similarly, you have to, you can see in round robin algorithm, there are some drawbacks are there. For example, I can say you are only following 1, 2, 3 order without looking into the execution time, whatever given in this particular matrix. So in order to avoid that, we have another algorithm that is called as list scheduling, or we call as cloud list scheduling. Okay, so list scheduling says that you have to find the minimum execution time for every task. For example, minimum execution time for task A, it is 2. So it is assigned to the first cloud. Minimum execution time for task B is cloud 3. So we assign to cloud 3. Minimum execution time is cloud 2. So it is cloud 2. Minimum execution time is cloud 3. So we assign to cloud 3. Minimum execution time here is cloud 3. So we are assigning to cloud 3. Minimum execution time here we are getting 2. Okay, second cloud. So it is second cloud. Minimum execution time is 4. So it is assigned to third cloud. Minimum execution time is 2. So it is assigned to first cloud. Minimum execution time is fast. So it should be fast. Okay, it is assigned to first cloud. And 846, the minimum is 4. So it is assigned to the second cloud. And 937, the minimum is in cloud 2. So it is assigned to cloud 2. And 2, 3, 4 case, the minimum we achieved in cloud 1, so we assign to cloud 1, right? So in this way, we are assigning the different type of task to different clouds, right? Wherever you are finding the minimum, you have to assign. Okay. So in this way, you can do the task scheduling with multi-cloud environment. Okay, multi-cloud environment where you can use also artificial intelligence, right? You can make predictions. You can see that which cloud is more busier. Okay, and in which cloud you are getting less execution time. Some predictions also we can do by the help of some machine learning techniques we can apply, and we can find appropriate values. Now, there are some couple of workflow scheduling algorithms are there. The workflow scheduling algorithms are based upon a single workflow. They are based upon a single workflow. Earlier we have seen it is based on, okay, it is based on, we have seen it is based upon multiple workflows. In the previous example, it is a multiple workflow, so it is too complex. But here we are talking about a single work. So in a single workflow, you can see here we are given with I think 6 number of tasks: T1, T2, T3, and T4 and T5, T6. Okay, 6 number of tasks. What you have to do? We have to assign this 6 tasks to, let's say, 3 clouds. Okay, and you can see there are 2 times we are maintaining here. 2 type of time. One is called as computation time, which is written within the circle. Okay, another is called as communication time, which we written in the rectangle. One is computation time, another is called as communication time. So earlier cases we have not considered communication time. If you go back to this particular case, we are not considering communication time. We consider only computation time. Okay. So T1 takes 5 minutes of time. Again, it is assigned to homogeneous processors, right? Means T1 is assigned to, if T1 is assigned to C1, it is taking 5 minutes of time. But if it is assigned to C2 also, it is taking 5 minutes of time. That's why the configuration is homogeneous. But in the previous case, the configuration is heterogeneous. So given a workflow, how to assign these tasks, in which order you are going to assign the task, that is more important. So what I will do here, the first measure that we are applying, that is called as T level. Okay, the first measure we are applying, that is called as T level. Okay, T level is called as top level, or it is also called as soon as possible. So if you calculate as soon as possible of each and every task, so you have to calculate their computation time. You have to look into their communication time. You have to consider the computation time of entry task and given task, communication time of the entry task, but you will not consider communication time of the given task. So T level finds entry task to the given task. Entry task is same for all other tasks, right? For all the tasks, entry task is same. That is T1. So if you want to find T level of, let's say, task T3, so you have to calculate T1 to T3. Okay, T1 to T3. So the computation time you have to calculate. Okay, and for all the tasks, for entry task you have to calculate, given task you will not calculate. Communication time you calculate for entry task, not in the given task. But if there is a multiple path exists in between T1 and T3, you have to consider all the paths and choose the maximum one. So let us see one example. For example, let us target T3. Okay, if I target T3. So T level is calculated based upon the entry task. Entry task is T1 to the given task, that is T3. So in order to reach T3, you can directly reach through this particular path, or you can reach through this particular path, right? So if you do reach directly, so it is, okay, I'll take the, let's say, leftmost path via T2. So if I go T1, T2, T3, so it is nothing but 5 plus 4 plus 7 plus 12. I am not going to consider the computation time of T3. Okay, is for T level. So if you calculate this one, you will get, I think, 9 plus 7, 16 plus 12 is 28. Similarly, somebody can directly follow T1 to T3. So it is 5 plus 3. So we will not consider this T3 here. So I'm getting 8. So there are two paths. One is 8, another is giving 28. So I have to select the minimum one. Sorry, I have to select the maximum one because it is top level. Some case you have to take minimum, some case you have to take maximum. But this case I am considering the maximum one, that is 28. Okay, like that you can calculate T level of other task. Once you found the T level of all the tasks, for example, if you calculate the T level of T1, so it is T1 to T1. Okay, so you are not going to consider the computation time of T1, so it is 0, right? So once you found this one, you have to order the task based upon the earliest T level. So earliest T level is T1 first, then T2, then T4, then T5, then T3, then T6. So this order you have to follow while you are assigning these tasks to a set of clouds. Okay. Now, if you go for bottom level case, instead of taking entry task to the given task, we are calculating given task to the exit task. So exit task is same for everyone, that is T6. Okay. So you have to calculate given task to the exit task. And in this case, computation time of the given task is considered, exit task is considered, communication time of the given task is considered, as well as exit task is considered. And there may be also chance that we have multiple path from a particular task to the T6. So if multiple paths are there, you have to select the maximum one. Okay. So let us see. So if you go for bottom level, suppose I am calculating bottom level of, let's say, T3. You can calculate for others. So it is saying given task T3 to exit task, that is T6, right? So T3 to T6. So if you calculate T3 to T6, that is B level. Okay. So what you will do? You will consider, is there any multiple path? Here I think there is no multiple path. There is only one path. So T3 case, it is 3 plus 4 plus 8. So it is 7 plus 8, you are getting 15. Okay. But if I take T4, so I can go for T4, T5, T6, which is nothing but 4 plus 9 plus 2 plus 5 plus 8. So you will get, I think, 13 plus 2, 15, 28. Yes, we are getting 28. And you can also follow this direct path. So direct path is T4 to T6. So we are getting 4 plus 11 plus 8. So you will get, it is 23. Okay, so there is two parts. So once you determine the B level of all the tasks, you have to select that select a particular task, or you have to order the task based upon highest B level. So highest B level we are getting in the case of T1. Then after T1, the highest B level is T2. Then next highest is T4. Then T3, T5 in any order because there is a tie, and then T6. So in this order, you are going to assign these tasks to number of clouds or number of machines. So if you are given with 3 machines, then you can assign them in this particular order, but you have to follow the precedence constants. You cannot execute simultaneously. Dependency you have to honor, right? Now there is another level that is called a static bottom level. So it is calculating given task to the exit task. So previously also we have seen B level, right? B level case also it is given task to the exit task. So what is the difference between B level and S level? So B level case, you are considering the computation time of the given task and exit task, and communication time you are considering. In the case of B level, you are considering communication time of both given task and entry task. But here you are not considering the communication time of given and exit task. But if there are multiple paths that exist, then we need to consider multiple paths and we have to select the maximum path. So let us go for T4. Okay, if I go for T4, so T4 is my given task and exit task is T6. So T4, T5, T6, there may be one path, or there may be another path, that is T4 to T6 directly. So if you follow this particular path, you will only consider the computation time. If you consider the computation time, it is 4 plus 2 plus 8. 4 plus 2 plus 8, you will get 14. Yes, we are getting 14 here. Or if you follow the direct path, it is 4 plus 8. So you will get 12. Right? And you will choose the maximum one. Okay. Similarly, you can calculate for all other tasks. Okay. Like suppose I'll calculate for, let's say, another task, that is T2. So T2 to T6. What are the possible ways? You can go for T2, T5, T6, one path, or you can go for T2, T3, T6. So if you follow this path, it is 7 plus 2 plus 8. You will get 17, right? If you follow this particular path, it is 7 plus 3 plus 8. So it is 18. So out of these two paths, you have to select the maximum path. The maximum path is 18. So we are selecting that one. So in static bottom level, once you calculate for all the tasks, you have to select the task. You have to order the task based upon highest static level. Highest static level is T1. So T1 is scheduled first. Then highest is T2. So it is scheduled next. Then T4. Okay. Next T3. Then T5. Then T6. So in this order, you are going to assign to the club. Okay. So the next measure is ALAP. That is called as late as possible. Which says that how much time the execution of the given task Ti be delayed. How much time we can delay the execution of a particular task, that is based upon ALAP. And it is doing the reverse order. So it is calculating from exit task to the given task. Exit task to the given task. So if you find as late as possible is calculated as critical path minus path between the exit task and given task. So if you calculate the critical path is the longest path from the entry task to the exit task. Critical path is the longest path from entry task to the exit task. If you find the longest path, you will get the longest path is 43. Okay. So once you find the critical path, you have to subtract path from exit task to the given task. Here you will consider the computation time of both the task, exit task and given task, communication time of entry task and exit task. If there are multiple paths that exist, then you will choose the minimum one. For all other case, you are choosing the maximum one. Okay. So if you go for it, for example, I want to calculate for T3. So my critical path is 43. 43 minus exit task to the T3. Exit task is T6. So T6 minus T3. So it is 8 plus 4 plus 3. So it is 43 minus 12 plus 3 is 15. So how much you will get? You will get 28. Similarly, if I calculate for T4, okay, T4. So it is 43 minus, you can go this way or you can go this way. So 43 minus 8 plus 11 plus 4 is one solution. Or you can say 43 minus 8 plus 5 plus 2 plus 9 plus 4. So if you calculate this one, I think it is 15 plus 8 is 23. So you will get 20. Okay. And 40, if you take this one, so 8 plus 5, 13 plus 2, 15, 9, 24, 28. So if you subtract 28, you will get 15. But you will choose the minimum one. That's why I'm selecting 15. Okay. Similarly, what you can do, you can calculate for other tasks. For example, let me show you another task for T2. I'm calculating for T2. So 43 minus, if I follow this path, 8 plus 5 plus 2 plus 8 plus 7. That is 1. And if you follow this particular path, then 43 minus 8 plus 4 plus 3 plus 12 plus 7. Okay, so how much you will get here? You will get 15 and 15. Okay, 30. So we will get 13. Yes, we are getting 13, 42. In this case, 43 minus, if you sum this value, 8 plus 12, 8 plus 4, 12 plus 3, 15, 27 plus 7. Okay, so you will get 34. 34 means you will get 9. So it is 9. So once you determine as late as possible for all the tasks, what you have to do? You have to select the minimum ALAP. So minimum ALP you are getting for T1, then the minimum one is T2, then the minimum one is T4, then T3, then T5, then T6. So in this order, you have to assign the task to the cloud. So there are different measures we have, but I am telling you some base measure, that is T level, B level, S level, and edge level is possible. So this order you have to follow to assign the task to the cloud. Okay, so what we have discussed in this session, I told you about the difference between resource allocation and task scheduling. Followed by I told you the difference between lease, task, job, and application. Then we started discussing about different type of leases: AR lease, best effort lease, immediate lease, negotiated lease, best effort with primitive, best effort without primitive or non-primitive. Then we discussed about several resource allocation algorithm. We specially discussed about one of the base algorithm which is available in the Open Resource Manager, that is HYGEA. Then we discussed about the DPS algorithm, and we see the performance of comparison of DPS with HYGEA. Then we discussed about ALT array algorithm, and these three algorithms can be compared with the number of accepted leases, number of rejected leases, and leases insisting rescheduling, lease rescheduled. We have seen these four measures. Then we discussed about the fairness algorithm, in which I told you the frequent arrival of advance reservation lease is going to be a problem for the best effort lease. So we have to make some fairness. Then we discussed about the posted price model, in which we take the number of tasks as number of resources, and we perform the mapping of the task to the resources. And we also discussed about two different multi-cloud task scheduling algorithm. One is round robin, another is lease scheduling. And we have also seen also in workflow scheduling some of the important measures that are taken in the cloud. That is T level, B level, S level, and as late as possible. So in which you can find the ordering of the task in different ordering of the task you have to determine. Then you can assign to different clouds. These are some of the references. You can, if you are interested, you can go through it. Yeah, thank you everyone. If you have any question, you can ask.